Okay, so let's draw out our anhydride, and let's think about, we have our, sorry, that's methyl 2 NH. So we have our nucleophile here. It's going to come in and attack that carbonyl carbon. We break the carbon oxygen double bond. So we've broken that. We give O minus. Then we have our NH Me2. Okay, so what we mean by that is that this nitrogen now has two methyl groups and a positive charge. We can then deprotonate to give just the two methyl groups left, and then we can reform that carbonyl bond, the carbon oxygen double bond, and lose this carb anion as our leaving group. So we end up with our new amide plus this carb anion as the leaving group. Okay, so that's, we had a bit of a choice there, but it was reasonably simple. What we're then going to move on to now is just looking at some examples where the first step of the reaction is pretty straightforward. We've done it before with the aldehydes and ketones, but then once we've formed the product, other things can happen, and we'll have a look at those. So we'll start by looking once again at hydride as a nucleophile. So if we take a hydride from our complex metal hydrides, remember, and we have something which has a leaving group, so an ester that we can make into a leaving group, an acid chloride, a carboxylic acid, any of those, we need to remember. So we've got our AlH3, so our lithium aluminium hydride. Okay, so this is lithium aluminium hydride. Okay, just as a shorthand we'll need in a minute. We're going to take the electrons from this bond with the hydrogen to give us our source of H minus. We then break the carbon oxygen double bond. What that would give us is this O minus. We've got our leaving group, we've got our hydrogen. If you remember from the previous examples with the aldehydes and ketones, this oxygen can then complex. So we then end up with O, Al, H3, Li. This has a plus, this has a minus. We have our leaving group, we have our hydrogen. Now, when we just did the ketone and aldehyde example, what we then saw was that this complex can then react further with another molecule of ketone or aldehyde. But in this case, we have this leaving group, so that changes things a little bit. What can happen here is we can reform the carbonyl from that bond, kick out the leaving group, and that gives us an aldehyde product. Plus we've got our AlH3 again. And what we can then see is, well, we've got a slight problem now, because we have in our reaction mixture our starting material, which is a carbonyl, which will react with a hydride source, and we have our ketone or our aldehyde, which we also know will react with the lithium aluminium hydride. And what we'll see right at the end of the reaction is, depending on what the L group is, the aldehyde could be more reactive than the carboxylic acid derivative. So if our aldehyde here is the one that's most reactive, this is going to react with the lithium aluminium hydride, and what we'll ultimately end up with is adding two hydrogens to that, along with the one that we have. No. We can add, we've added this hydrogen, we would have the oxygen where we would add another hydrogen, and then if we turn that into an OH, we end up with a primary alcohol. So what that tells us is, if for example we took an ester group, then, so if we had this as an O ethyl, what this would give us is we would move from the O ethyl to an aldehyde plus ethanol, because our leaving group here would give us the ethanol, and then this would go on to a further reaction with the lithium aluminum hydride, the ketone, to give us our OH. So we would end up with one alcohol, two alcohols. So we can end up with two different alcohol products from the hydride reduction of that carboxylic acid. As always, it gets slightly different when we add nitrogens into the mix. So let's have a look at the example with the nitrogen. So we have our NHR. We add our lithium aluminium hydride. So the pair of electrons here go up to attack the carbonyl carbon. We break the carbon oxygen double bond. With our O minus up here, we've still got our NHR here. And we've added our hydrogen. Again, we can complex to the aluminium that comes out of this. Give us this kind of complex. And then at this point, the nitrogen can reform a carbon-nitrogen double bond, so a kind of imine, and we can have this leave. So what we then end up with is some kind of iminium cation, which we can again take H minus, react with this, and ultimately give us, we would have added two hydrogens and end up with an amine. So when we take lithium aluminum hydride with an amide, we would end up with an amine product rather than the alcohol products that we ended up with, or the two different alcohol products. Here we just end up with one amine. So that's the example of hydride. We can also think about carbon as a nucleophile. So if we look at those Grignard reagents, again, very, very similar to what we started with, where we have our R group with some kind of leaving group. And again, that can be any of those ones that we've been looking at before, whether it's a carboxylic acid, an ester, or an amide. We react with our Grignard takes the electrons out of this R magnesium bond, reacts with the carbonyl carbon. We break the carbon oxygen double bond. We end up with our O minus, MgX plus complex. We have our leaving group. We have this other R group. We then reform the carbonyl carbon, kick out the leaving group. That gives us our ketone, and then of course we have the same problem. We've got the same problem because we have one carboxylic acid here, we have a second carbonyl here. Both of them can react with the Grignard reagent, and I said, as we'll find out in a minute, the ketone could be more reactive than the starting material, and so if you add another molecule of Grignard here, what we would end up is with adding another R group to this, and we would end up with another alcohol. So it just shows, those last ones are just there to start showing you that, you know, the reactions are reasonably simple, okay? They're the same reaction mechanisms, but we need to start thinking about if we react to carboxylic acid derivative and it gives us another kind of carboxylic acid or a carbonyl group, could that carbonyl group go on and do more reactions? So what I'm going to do now is summarise the mechanisms we've covered. So we have done the reaction of nucleophiles with some simple carbonyls. So by that I mean aldehydes and ketones. We've then done reactions of slightly more complex carbonyl derivatives or carboxylic acid derivatives. So they are the carboxylic acids, the esters, the acid halides, the anhydrides and amides. So we've got 7 different carbonyl groups there, but hopefully you'll see that the reactivity is driven very much by the delta positive of the carbonyl carbon and breaking that carbon-oxygen double bond. It's just depending on whether you have these more complex ones, depends on whether we then go through different routes to our reaction mechanism. We've then had a number of different nucleophiles. We've had oxygen, so water and alcohols. We've had amines. We've had hydride from the complex metal hydrides. We've had carbon, we've had Grignards, acetylides and cyanohydrins. And finally, we've had thiols. We've just touched on those, but they follow the same patterns as the oxygen nucleophiles. So what you've got there is several different kinds of nucleophiles and several different kinds of carbonyls. And you can't learn all of those reaction mechanisms by rote. You can't say, right, what would be the movement of the arrows with an aldehyde with an amine or an aldehyde with a Grignard. What you need to do is see where those mechanisms are similar and where they differ, and understand that fundamentally the start of the reaction is nearly always the same. That first attack to that carbonyl carbon happens the same every time. It's once you get to that tetrahedral intermediate, you have to decide, are there choices to make? Is there a leaving group present? Is there a leaving group you can make? So do you just reform your carbonyl and kick out a leaving group, or do you have to protonate your oxygen, for example? So if I summarise those mechanisms, what I mean by that is, let's take a standard simple aldehyde, so a simple carbonyl molecule. What you can do is you can take your nucleophile, it always reacts with that carbonyl carbon, and you always break the carbon-oxygen double bond. That will give you your tetrahedral intermediate. Okay. Now, if your nucleophile happens to be a good leaving group, then you can reform your carbonyl carbon and kick out your leaving group, your nucleophile. What that will do is take you back to where you started. So that is showing that lots of these reactions can be reversible. It depends on your nucleophile. If your nucleophile is not a good leaving group, so when you add hydride, for example, when you add the Grignard, for example, then you can't just reverse the reaction because your nucleophile wouldn't leave, in which case you add some kind of electrophile, usually a proton, and you get this addition reaction where you've added your nucleophile and you've gone from having a carbonyl to having a tetrahedral species. So that kind of sums up the simple stuff and thinking about, is your nucleophile a good leaving group or not? So if it was an alcohol or water, for example, the nucleophile itself could be a good leaving group, so therefore you might have a choice between going and making your tetrahedral species, so things like the hemiacetals and the acetals, or just reversing the reaction, going straight back to the carbonyl you had to start with. It gets a little bit more interesting when you replace the hydrogen with some kind of leaving group. Again, that start of the reaction, very similar. You react with the carbonyl carbon. Sometimes we might have had to activate that carbonyl carbon, and you get a tetrahedral species. Okay, if your L is a really good leaving group, then you can just reform your carbonyl carbon and make the leaving group leave. And you can see that that's exactly the same movement of electrons, the same curved arrows as on the example at the top. So although there seems like there's lots of mechanistic chemistry here, there isn't really. A lot of it is very, very common to all of those different functional groups, all those different carbonyl groups, all those different nucleophiles. What you need to start to look at is understanding what makes something a good nucleophile, whether you need to activate your carbonyl group. Is there a clear acid present? is this under basic conditions, and then learn or understand how, you know, acidic conditions changes the reactivity and then the reaction pathway you have to go through. The other thing you need to work out is if you were making more than one carbonyl, which one would react. So let's have a look at the reactivity of the different carbonyl groups. And the main thing is the reactivity of that carbonyl carbon is dependent on the substituents that are attached to it. And it depends on their ability to stabilize the delta positive charge on that carbon atom. So the more that delta positive charge can be stabilized, the less reactive the carbonyl carbon will be. It also depends on if your substituent is a good leaving group or not. So what we're going to do is go through the ones that we've seen over the course of this lecture series and put them in order. We're starting with the most reactive first. So the most reactive are the acid chlorides. So the acid chloride has a highly electronegative halogen, which means that that is going to pull electron density away from that carbonyl carbon. So by having the chloride there, it makes this carbonyl carbon far more delta positive than it would have been without that chlorine. And the chloride ion is also a very good leaving group. So those two things together mean that this is going to be a really reactive carbonyl species. The next one is the anhydrides. So these are also very reactive. So the anhydrides, if you remember, are these kind of double carbonyls separated by an oxygen. One of the reasons is that that second carbonyl group is very electron withdrawing. Imagine, if you can, you've got that lone pair of electrons and you can resonance stabilize them or draw resonance structures where that oxygen gives off its lone pair or delocalizes them across there, gives it a positive charge. Now you can see, well, that positive charge is going to be really unfavorable for that oxygen. How's it going to get some electron density? Well, it's going to pull it away from that carbonyl carbon. So that carbonyl carbon is going to become even more delta positive. It's an example of an electron withdrawing group, just like when we were looking at the aromatic chemistry. And then finally, once that the reaction does occur, what we end up with is this leaving group here. And again, it's got this resonance stabilization. You can move that double bond, or that you can move that lone pair of electrons, that negative charge, across the two oxygens. That makes it really stable, and that makes it a good leaving group. So the anhydrides are next in the reactivity behind the acid chlorides for that reason. After that comes the aldehydes and ketones, okay? And we covered this right at the start of the lecture series, and we said that they're very, very similar, but the aldehyde is more reactive than the ketone. And that's because in the ketone, you've got these two groups which can push electron density into that delta positive carbon and stabilize it. In the aldehyde, you've only got one that can do that. Therefore, the delta positive, the carbon here, is much more delta positive in the aldehyde than it is in the ketone, and that makes it more reactive. The other thing to note is it doesn't have a good leaving group. The hydrogen, or the R group, which is some carbon chain, the hydrogen and carbon by themselves are very, very poor leaving groups. Okay, we then move on to esters and amides. Okay, so again, incredibly similar in their structure. It's just in one you have an OR group, in the other one you have an NH or an NR group. And what we know, or what I can tell you, is that esters are more reactive than amides. And we cover this a little bit, but we're just going to look at it again. Think about it. It's the delocalization of the lone pair that will stabilize the positive nature of the carbon. So we can think about that the electrons from here, this lone pair of electrons, can be delocalized across to that oxygen. So we can draw a resonance structure that says this is O minus, this is OR plus. And again, if we think about it, you know, if we think about, you know, here is our carbonyl carbon, and we've got these pi bonds, okay? We've then got this going off to another oxygen here, which has a pi bond. You can see that these can all overlap with each other. And what that means is, although predominantly the electrons are going to reside kind of on the two oxygens, the carbon gets a bit of a share of that. That lone pair of electrons that are here, that aren't present in the aldehydes and ketones, can be shared a little bit with the carbon, and that makes it less reactive than the aldehydes and ketones. Now, why is it that the esters are more reactive than the amides? Well, that's just down to the fact that the oxygen isn't really going to want to delocalize its electrons as much. They're more electronegative. So in this situation where the carbon gets a bit of a share of them, they are predominantly going to sit with the oxygens. So the carbon will get a tiny, tiny share. In the nitrogen example, when you've got the nitrogen here, the same thing can happen. And what we know is nitrogen is more willing to do that delocalization. So if it's more likely to delocalize into it, this carbon in the middle is going to get a little bit more of a share of those nitrogens. Again, just having a little tiny bit more of a share of those electrons means that it is less delta positive, which means it's less reactive.